few announcements. Homework 5. Are we done with that? Done? Demoed? Was it hard? Was it harder than 4?
Yeah.
Harder than 4. You guys are experts at TensorFlow now. Maybe we should ask that in the exam, TensorFlow. I found it 5 to be a lot easier than 4. I mean, if I'd be a student, so to speak, if I do the work. Because 4 requires this TensorFlow setup that really needs time to spend on. In fact, in industry, if you work on something like that, you'd spend the first at least 4 months in that group playing with TensorFlow and with their particular setup in TensorFlow. Because there's so many things you can do there. While homework 5 is kind of straightforward, I think.
Or you can demo in the internet. You can directly look at.
What?
4 is easier to find the example in the
Right.
internet.
But then can you explain exactly what's happening in that setup? You can copy paste the code and run it,
Yeah.
but can you tell exactly what's going
So I
on?
don't think I think the 4 in the understanding is more challenging than 5.
Yeah,
But
I agree. I
5
agree.
you need to
I
run
look
more.
at some TensorFlow. I'm not working with TensorFlow on a day-by-day basis myself. I know what neural networks are, and I've been around machine learning data mining before TensorFlow started, before deep learning started, where we just had neural networks and they were not so useful. And I still find it hard to understand how to set up TensorFlow. I'm lucky I have some PhD students who do that for a living. That's what they live and breathe, so they can help with that. But there is a homework 6. The due date is that you have to demo it. So there's no really a due date. In fact, I'm not really keen on deadlines in general. As long as you demo the homeworks and the TAs have enough time to put your grade or to give you feedback and you fix it, that's fine. So probably we're going to discuss with TAs what's their schedule. After the 25th, that's another thing here, there's an exam. Wednesday the 25th, what is it, 12 p.m.? Right? Bring a computer and a charger in that room. You have to have a computer and a charger that's set up to run the kind of things that we've been running, like Python and PCA and TensorFlow and all of that, right? After the exam, I'm not sure how many demos we can do on homework 6. We certainly are going to allow after the exam to do just the demo, as in I'm coming in and I'm getting a grade. We may not be able to allow the feedback loop, as in you come in, it's not good enough, you have to fix it. That may not be possible after the 25th, okay? But if you just have to give a demo of homework 6, sure that it works, it's fine. On homework 6, there's only 2 problems, one recommender system and one social graph problem. The social graph problem, we have the graph, it's downloaded from a website, Friendster or Flickr, I forgot which one it is. That graph, you can try to do community detection on that graph like the problem asks. I think the graph is too big for your computing power. So what it says there, use the graph that it's not available yet, the smaller one that I'm trying to curate myself. Now, if you really want to take on the big graph, the graph is actually very old. That's like from like 10 years ago, 9 years ago. But the graph, so the problem 1 is recommender system. This is very small data set, movies. Problem 2 is community detection in the social graph. If I remember correctly, this graph has V about 80K and E about 5 million edges. And now, I'm not sure whether this algorithm that I'm asking you to implement, the one I'm going to discuss today further from last time, it's implementable on the kind of computer you have. So I'm gonna make available a smaller graph, a subset of this graph. I'm gonna delete some edges and vertices from this graph, make a smaller one that surely can be run on a computer like a laptop. But if you want to solve the homework problems today, you can take on a big one, okay? And the other thing that I need to bring your attention to is the trace evaluations. That is where you say what you think about the course and about me and everything that's good and everything that's bad. How many people have done trace evaluations before? As in, this is not the first time you do it. Okay, so the people who didn't raise their hand, this is the first time you heard about trace evaluations? Because if you do, I have to give you the spiel. It's a university requirement. I prefer to skip it if you did it before. Trace evaluation is a system where the students come in. You must have gotten an email by now from the registrar that says, please evaluate Virgil for in the CS 6220 or 5230 course. That's this course. And there's a bunch of questions. Some of them you have to write a plain text comment. Some of them you will put a scale grade between 1 and 5, things like that. A lot of questions are very focused. How do you feel about the lecture? How do you feel about the homework? How do you feel about the textbook? How do you feel about materials, interactions with TAs, on and on and on and on. And there's one in particular that says how you feel about this instructor. Is he able to teach? Is he a nice person? You know? So here's my recommendation for you guys. You should have a personal point of view. In our society, especially lately, everybody tries to be what's called politically correct. I'm not going to get into what that means, but people try to be nice in the sense that's being approved to be nice. What I mean is like the kind of things that are accepted today and not accepted today were not exactly the kind of things that were accepted 50 years ago or not accepted 50 years ago, right? Things have changed. And then other kind of things that will be accepted 50 years from now, so not accepted 50 years from now. I say ignore all that. Just be plain yourself. Don't worry about being correct or incorrect or if you have a problem with that's happened in this course, you should put it there. Or if you don't feel comfortable, put it there. You can send it to me on an email. And if you don't want to send me in a way I can know who you are, then you can find an anonymous way to send me an email. Hey, I'm a student in your class, but I don't want to tell you my name. It's fine. Be yourself, number one. Number two, be honest. Say the good things, because we love to hear the good things, right? Who doesn't? But say the bad things too. What you think it didn't work so well, or what you would like to see improved. These bad things are actually more important than the good things, because while it makes us feel bad if you say bad things, it's the kind of things that we can act on to improve. In next year, if I teach this class again, there will be maybe a better version of this class. All classes improve with time. It is true. The 6th version, 8th version of a course, it's usually better than the first one. Now, for that to happen, that's my last point about trace evaluations, you have to be constructive. It's not enough to say, I really didn't like the homework. Like, I prefer no homework. That's not going to change in the next version of the course. There's still going to be homeworks, okay? So I don't like, I don't know, I don't want to say anything funny, but I don't want the way Virgil dresses up, okay? That may change or may not change, but it's largely not up to university standards or me or. So I think you should be constructive. If you don't like something, you should explain why and why you think something else would have been better. I already got a lot of feedback from you. The people who came talk to me one-to-one in person and say, I think we're using, for example, too many libraries. We call these libraries, but we don't implement enough ourselves. That's a valid comment, and you could write that in the trace evaluation. You should write that if you feel that way. Keep in mind that this course is designed to be a rather introductory to data science. So out of all the classes that there are there, we view this class as a more earlier course that people can take without much prerequisites, as opposed to the machine learning class, which we view as a more later course, which people can take with more prerequisites. So especially, I mean, I appreciate this comment as being very pertinent, but you should put yourself, you should ask if your background in judging those things is an experimented student. If you already took, for example, machine learning, and if you're already working data science, you might feel that this class is a little too soft. That's correct, because it's designed for people who did not take machine learning and who did not work in data science and data problems before. Yeah, we gotta start somewhere, right? So that being said, how many people feel trace evaluation for this course? Anybody? 1, 2. Okay, please. It makes me look good if a lot of you feel it. Even if you say bad things, at least I can say, look, a lot of people feel it, right? Even if the score is not that good. But be honest about what you think worked well and what did not work so well. Okay, so we have to deal with graphs today. I'm not going to talk about recommendation systems because the homework you have, it's quite simple on that. But I will talk about what we started last time. Bit of a new one. I should say that's part 1 of what we want to do. Depending how much time we have, we may do other things. So if people are remembering what was the idea here, we were saying as a toy example, right? This is, I think, the same example we had last time. There's another edge here. We want to detect communities. That is nodes that are tightly connected inside the community, but loosely connected to other communities. This is important in social media because social media graphs tend to look like this. There are other graphs who kind of don't look like that. In fact, most graphs are not local graphs like the social graphs. Trade graphs, money graphs, geographic maps, hierarchical graphs, even the web graph is not so local. There are some nodes that are local and some nodes that are more global. But social graphs definitely tend to look like this. While in social graphs we have entities I mentioned before, like a famous athlete or a famous company that are having a lot of connections. Those are not really social connections. I made this case last time that if Cristiano Ronaldo, a very famous athlete, or LeBron James, or a famous company, is friends with 20 million other people, they're not really friends in a social sense. They're simply a way for information from Ronaldo or the big entity to diffuse to the other entities. Information only flows one way in that sense. And it's pretty much a medium of advertisement, if you want. Not an advertisement in a commercial sense, but in a, why Ronaldo would put something on his Facebook page or Twitter or whatever. What he puts there, it's not personal information compare an entity like a big athlete with yourself. When you put a picture, you put that picture presumably thinking that your friends or somebody in your family or something like that would appreciate the picture on a personal level, right? Most pictures that people put on Facebook are not for public use. Somebody who's not your friend or family would probably, even if accidentally sees the picture, would not appreciate what's in the picture, right? It's just a regular picture, happen to be you. It only has value for somebody who's like your friend, or some like your mother or brother or somebody in your family. That's a social connection, by definition, from the word social. When Ronaldo puts a picture with him, or a picture of a product that's related to him, or something like this, it's not that kind of social connection. Many people would see the picture And perhaps the picture is very spectacular with him doing something in the sport that matters a lot. The people who follow Ronaldo will probably appreciate it, but not on the same way you appreciate your cousin's picture. It's not a social connection. Okay? It's the same kind of information flow or connection that happen if there is a website of Ronaldo or of a team that Ronaldo play with, and people are checking up regularly that website to see what happened, right? In some sort of way that's more like a news portal about Ronaldo than in a commercial sense than it is a social connection. So I'm going to ignore for now these nodes that have that property, and I'm going to focus on the social connections. Those are much more local, right? 99.999% of entities on Facebook have only local connections in that sense. So how do we find them? How do we find those groups? Community. We had this idea last time. We explored a few things together here, and we said one way to go by, which is this algorithm, is to find these edges. Right? So the idea of this algorithm, if I could find this edge, in this example, and this edge, I would find the communities. So the idea of this algorithm is find edges between communities and remove them. Again, intuitively speaking, the idea is if I can remove those and then I look at connected components or something like that, then I'll find these components. It's quite easy to call traversal algorithms and find the components once these edges are removed. Right? We all remember BFS, DFS, Dijkstra for shortest path, right? So on and so forth. So what we're going to need is a notion of betweenness. Of an edge ij. And the idea is that if this is high, then implies it's an edge between communities. And if it's low, then it's not. And further, before we get more technical, we said this has to do with what? We still have common sense. Notion of betweenness. Why this edge has a large high betweenness? This score. This is a score that I'm trying to compute. How do visually, it's easy to spot, right? Those are nice big connected components, and this is an edge between them. But in a more like graph mechanical perspective, how can I characterize this edge? A lot of paths from here to here have this edge in common. So this betweenness, it's kind of a bottleneck. Means if you want to pass from here to here, you have to use that edge. There's not much option left. So we're going to say informally this is a fraction of shortest paths. Shortest paths, say from S to K. Shortest path from S to K that passes through edge. Let's call it IJ. Okay, that's what we want. How do we get there? So I'm going to follow the exposition that's in the book. And first things first is the notion of an edge is tight. That's how it's called in the book, if belongs to a shortest path. So here's an example that's there. There are a bunch of nodes here. The book, I think it's misleading in that it calls these nodes, labels them with integers, and it also labels the edges with weights, which are integers, and that makes this confusing drawing. So for me here, I'm going to try to avoid labeling the nodes. If I label them, I'm going to call them A, B, C, D, as opposed to 1, 2, 3, 4. So now we have some edge weights: 1, 3, 6, 2, 2, 4, 1, 2, 1, 2, 3. And so we want only shortest paths. That means tight edges. So we're gonna draw this again, but only putting the shortest path. Before this, perhaps we should remind ourselves something about shortest path. All days, not the people who take the algorithms class, that's very fresh for us, but the people who are not taking recently an algorithms class. Just a simple thing about shortest path. That is, if I have some starting point S, right, and I have a shortest path to some node, let's use the notation from the book I, and then I have some J here, right, and this is the shortest path to J. So this whole thing is the shortest path from S, let's call it Sj, shortest path to Sj, passes through I. Let's say pass last node I. So in this shortest path, usually when we put a wobbling line, that's a path. When we put a straight line, that's an edge. So we say the last node on the shortest path from S to J is I. What does that mean? That's equivalent to saying that the SP from S to J, as a value, is the SP from S to I plus the edge IJ. Just a reminder on how shortest paths work, and the shortest paths algorithm, including Dijkstra, will be based on this idea, right? That if I discover the shortest path through here, and I'm sure that that's the actual shortest path, and if this is the minimum edge or the minimum something, then I can expand and say I actually discovered the next shortest path through J, right? But I have to be sure that the one I have so far is actually the minimum. So in some sense, shortest paths algorithm will try to reverse this formula in a dynamic programming sense. This must be true at the end. If this is the shortest path from S to J, passes through I, this property must be true. So algorithms will try to say, if you already found this S to I, and you can evaluate what's happening if you add an edge there, then you are likely to discover the other shortest path that includes this one. Again, you may have to go home and recap Dijkstra, but that's how they work. And if all the edges are just 0, 1, as in I don't have weights, I can just use BFS to discover shortest paths. Okay. So with that in mind, let's say we start from here. This is S. And we only want to do shortest paths here. So is this edge 1 a shortest path edge? If I start in S, it is. How about this edge? Since I start from S, the shortest paths will be a tree starting at S, or a DAG if I allow multiple routes. If the shortest path is not unique, I have two shortest paths that end up in the same point, that will form a DAG, meaning it's not really a tree, but there's no cycles in it. Right? So that will happen here. This is an edge of 3. Is this the shortest path edge? If this is the shortest path edge, according to my equation here, what is the shortest path to this point? This shortest path must be 1, right? The shortest path here is 0 because that's what I started. So this is the SP value. SP equal 1. This, if 3 is the shortest path, then the SP to that point is 3, right? How about this edge, this 2? Is it the shortest path edge? Can I create a shortest path using this edge? Right, this way, right? How about this way? Is this way a shortest path?
No.
No. Only this way is the shortest path because 1 plus 2 gives me the shortest path value 3. So this is the DAG thing where it says from here to here, there's 2 shortest paths. One is the direct 3, the other one is a 1 and 2. So what we can write, not just the value of the shortest path, but we're also going to write the count. How many shortest paths are there? So in here, there's only one shortest path, right? Let's write this better. Shortest path is value, and then the count is 1. There's one shortest path. In here, shortest path is 3, but the count is how many shortest paths I have to go here? 2, right? There's 2 paths of size 3 that end up in this point. Let's keep going. So there's a vertex here. Which one is a shortest path to get here? In here, the shortest path is 1. If I use this edge, I get a 5, right? Is that correct?
Yes.
1 plus 4. If I use this edge, I get a also 5. So the shortest path here is 5, and the count is how many ways do I have to get here? Both edges are tight edges. They are part of shortest paths. So how many ways I have to get here? In here, how many ways do I have to get? 1. And from here, there was only 1 way. So that's a 1. In here, there were 2 ways. And I have 1 edge to continue. So that would be 2 going this way and 1 going that way. That's a 3. How about this edge 6? Is this part of the shortest path? Can I use that edge 6 to get a shortest path? If I use it from here, directly from the source, I get a 6. That's too big, right? Are you guys following me? Okay, so that edge is not there. And then if I keep doing this, let's see what we get. Is this the shortest path edge here? 1. This would be the shortest path, will now be 6, and the count will be 4. Why 4? It's how many count I have here, but it's only 1 way, I think, to get here. So the count is still 3 because there's 3 ways to get to here, and from here I have to go to this edge. So there's still only 3 ways. And in here I have an edge of size 2. That shortest path will be 7. Count will be 3. How about this edge? There is an edge here, this 3. Can I use this 3 somehow? Is it either this way or that way part of the shortest path? No, so I'm not using that. And then in here I have edges that are 2. That will create so this will be a shortest path of size 8, and the count will be, I can go through these 3 ways and use this edge, or I can go to these 3 ways and use this edge. So total is 6. Either one of those 3 ways, it's good, and then that edge, that gives me an 8. Oh, this 3 edge then. So this graph here is what the book calls the GS, which is only the tight edges, meaning the ones that belong to some shortest path. So the edges that are not on shortest paths are removed. Okay, so what else we have is this count number of shortest paths from S to J. So this C here, we call it in the graph, in the book it's called having a started source, how many shortest paths are there. That's the count we put on the drawing. We're gonna need another two things, so let's see. Let's say this is S, this is the shortest path, passes through I, and ends up in a node K. So this is a shortest path from SK. We're gonna call, following this notation, F SK of I is the fraction of shortest path from S to K passing through node I. So if I is truly a bottleneck, the node I, it means all the paths pass through I. It means this fraction will be 1. So this is a big number if it says it's a bottleneck between S and K. Similarly, I'm going to use the notation from the book to make it easier for you to read this at home. Okay? FSKIJ, it's the fraction. So now we have an edge here. Let's draw it again. S goes to I. This is an edge, J, and then goes to K. This is a fraction of same shortest path from S to K, passing through edge. This is a vertex. This is edge IJ. So one is how many paths pass through node I, and the other one is how many paths pass through edge IJ as a fraction of the total. The total number of shortest paths from S to K is the same in both cases. I have so many shortest paths, right? Now, which one is bigger as a count or as a fraction? The one that passed through I is bigger, or the one that passed through edge IJ? Which way? There's an inclusion here. All the nodes that are in one category, all the paths in one category must also be in the other category, but which way it goes?
All the paths in IJ should be in I.
Right. So all these paths here will have to pass through I, but not all paths that pass through I necessarily have to pass through some edge IJ, right? It might be that some shortest path follows a different, it passes through I, but not through the edge IJ, or it passes through J, but not through the node I, right? Can a node pass through I and J, a shortest path pass through I and J, and use the edge IJ? Right, so say IJ is a tight edge on this path because there's a shortest path that passes through it. Can there be another shortest path that passes through I and J, but not through the edge IJ? Is that possible? To have two shortest paths, both passing through I and J, one uses the direct edge IJ, and one uses some going around without the edge IJ. Is it possible?
If the edge weight is 0.
No, there's no zero edges. Is it? So some people say clearly, yes, I heard that, and some people bang their heads the other way, means no. So which one is it?
Possible this weights are the same. Yeah.
So can I have a bunch of nodes here 1, 1, 1, and this edge to be a 3. And then the shortest path, it's either 1, 1, 1 or the 3. Because to have two shortest paths, they must have the same total weight, right? Because that's why they're both shortest paths. If one of them would be shorter, the other one wouldn't be a shortest path, right? So that is possible. Okay, so now we have these definitions of fractions. And finally, what the book says, we want the following. Betweenness of a node I. This is betweenness. Betweenness of I. But it's all counted from the source S. So it's all from source S. This is like if you pay attention in algorithms, there's a single source, da da da, and then there is an all source, da da da. This is with a fixed source. So betweenness, it's the sum for all I, j edges that are tight of, hold on, that's coming later. Let's write that a little later. FSK I, so this is for all k not s. That's more like a definition. And then this is equal to all the ij tight. So this is a sum over all sum over all I. Then the other one is betweenness of I, j. Let's make sure we understand this formula. So those two are definitions that are saying if I have this bottleneck score, this is the bottleneck score for a vertex J, right? It's from all k's that pass through J, right? Starting from an S point. Say I want to sum them up because I may have multiple k's, right? There might be a K1, a K2, a K3. So there's a path to K1, another to A2, another to K3. So I want to know how central or how between S score is the J. Again, S is fixed here. So we're going to have to deal with multiple S's later. But I'm going to sum those paths that once they get through J, where else can they go? Remember that shortest path tend to form a tree or a DAG. So once you got to J, and you know there's a shortest path from S to J, everywhere you go from there following tight edges, it's going to continue with the shortest path from J. It's this principle that we had in here. Once you get somewhere and you didn't reach yet J, if that's a tight edge, then the shortest path will pass through I. So this in here is the same summation but for an edge. It says the betweenness or how tight an edge is has to do with, again, ij, how many paths pass through ij, and then follow up later on somewhere else. But then there's a relationship that says this guy here has to be the sum of all these guys. So how does that work? What is this saying for all I? It's saying if I fix this j, I may have a bunch of i's here, and they all have tight edges, right? So what is FSK? So what is this equation saying here is that if you want to compute the centrality of betweenness of j, you sum up all the ones that have these tight edges ij. You can obtain this betweenness or score for j by summing up all the betweenness of these edges here. Who's with me? At least following the story, say. No? Let's have some questions. What?
The second question. Is the second equation is summing up like outgoing edges of J?
Yeah, these parts are kind of like definitions, right? They're saying it's the sum of FSK values. It's saying sum of the other FSK value over the edges. There's not much there. It's just a definition of what the thing is. Don't you love it when a book uses the big B to sum up the small f's and the small b to sum up the big F's, right? So if you try to be confusing on purpose, you wouldn't do it that well. Anyway, but that's more like definition. Are you asking, the real question is this equality sign here. Why is it that this sums in here, the centrality of this node J, is really the centrality or betweenness score over all the tight edges that go into J. I mean the tight edges that follow this way. Tight edges again means what? There is a shortest path that flows through there to J. Remember, shortest paths form a DAG. If you include all options. If you run BFS or Dijkstra, you don't get a DAG because every time there is multiple options for the shortest path, they typically choose one, not keep track on all of them.
So, Rosa, like, what is the second equation?
This?
Yeah, that is
Sum.
sum of.
So this is the same equation, just not for a node, it's for an edge. It says the betweenness of an edge, or the bottleneck, how much of a bottleneck that edge is, has to do with all the paths that pass through that edge.
Oh, okay.
And it's the same concept for a node. Betweenness, how the book calls it, I call it bottleneck, or how important is it as a channel to, you're forced to pass through it. It has to do with how many shortest paths pass through there. Remember, these F's are really proportions. They're not actual. I mean, you can make them count if you multiply with how many paths are total, but they're really a fraction of how many shortest paths are. So then, what can we do next? How do we run this algorithm?
So second relation does not even care about K. So the equality does not care about the K. It's only of the incoming shortest paths.
Yeah, that's the whole point of being an equation. It says that whatever you got by summing these proportions, it's actually, you can just sum
It's only incoming.
over these edges and you sum everything, because everything must pass through these tight edges. Assuming this includes all the tight edges. That's what it says. All tight edges that are from I to J. Tight being there is the shortest path to J that passes through I as the last vertex. This would make some interesting problems for the final in algorithms, right? Right? And just think about that now. Some tight edges show that shortest paths have. This equation right here prove that this is true in a graph, right? Like that, by induction or something. That would be an interesting problem. Okay, so then back to this algorithm. What's the plan here? That's all calculations. I wanted to go over the intuition because then you're gonna implement this for the homework and you say, I have no clue what big B, small b that means. So there you go. There is another equation that is saying here's the, let's put it here. Bs of I is 1 plus this is the same sum like here, except it's for j. So that's the only difference. J, edge ij is tight. So this is over Bs. So what is this saying? I'm summing up the centrality of an edge over all the edges that are pointing to J. Right? This sum here, again, is saying sum up the betweenness scores for those three edges. What does it say to say sum up the betweenness scores from all the edges ij, but summing over j? So that's for an I, right? So this is saying you pick a point I now, that's Bs of I, centrality of I. It's saying that you can obtain that as a 1 plus 1. We'll discuss later where the 1 coming from. It's saying how much of a bottleneck this I is has to do with summing over all edges. What edges are those? Tight, that? This in here are all tight edges that are incoming to J, right? See the drawing incoming to J? Because I was computing the bottleneck in J. This in here is a bottleneck in I, and it says it's a sum of all edges bottlenecks that are outgoing from I. It's summing outgoing edges from I. It says, but only tight edges. It says sum up the outgoing edges of I, you get a bottleneck here. But there is a plus 1. Any idea where the plus 1's coming from? So these outgoing edges have to do with all the shortest paths that from I continue in my DAG to some other nodes, right? Because the shortest paths form this DAG, or tree if I don't have multiple options. Once I got the shortest paths to I, and I keep following tight edges, I'm still on the shortest path graph. But where is the plus 1? Remember, I'm not summing counts, I'm summing proportions. So plus 1 has to do with one of these f's that as a proportion is 1, right? So if you think about the definition of this BS, it's a sum of proportions, right? And this is the sum of all proportions over the edges, outgoing edges. That's all shortest paths that keep going to some other nodes, plus 1. Where's the 1 coming from? It's an obvious answer. Don't laugh at me. But why there's a plus 1? There is a 1 node here that all shortest paths include that node. I, all shortest paths through I will end up in node I. So what's the proportion of nodes that passes through I as shortest paths from S to I? Well, all of them, because all of them have to end up in I. That's where this 1's coming from. So let me put this in a different perspective. Are all starting from S? If I want to go through all kinds of nodes via the DAG, shortest paths DAG, what kind of nodes are there? There are several kinds of nodes. The nodes that I hit before I, some node here, those are not included in these calculations because neither I or J or anybody is on that shortest path. All shortest paths to an earlier node, they don't pass through IJ. So that's one category of nodes that are on this DAG, nothing to do with I and J. There is I and J then, and then there is all the nodes that are reachable from S with shortest path through I and J, and possibly through some other way. That's why we use proportions, because some node here might be reachable through I or through edge ij, but also reachable with the shortest path going around. So then there's a proportion. How many of them passes through ij, which is my bottleneck, versus how many shortest paths just go around. So you can think of the nodes of the entire graph as the ones that have nothing to do with ij. This f would be 0. As a proportion, none of the shortest paths through those nodes k, right? If k is here, how many shortest paths as a proportion passes through I or to j or through ij? None of them. So s is 0. There is the I and j alone for which the proportion is 1. And then there is other nodes later that you can get through ij or you can go around. And if you can only go through ij, the proportion will still be 1. But if you can go around, it's not 1 anymore. Okay. So I think that's how you have to set up calculations to determine this betweenness of an edge. And the ones that have high scores are the ones that you want to remove from the graph. Right? That's what this algorithm is saying. The moment you have a very high score, remove the edge from the graph. And then, so how do we do this algorithm? Once we have a plan, we remove highest Bij edge, and then we have to update the Bij on the other edges. This could be computationally very expensive. So there are some shortcuts for how to do this by setting up a little bit of a modularity and using the shortest paths already computed. If I keep track of the shortest paths, then calculations will get easier. Now that's not going to be included in your grading for the homework. Whatever you update these edges is going to be fine. The other way I can do this, which happens quite a lot in a lot of data problems, is to do batches. Once I compute the Bij scores, don't just remove one edge out of, how much did I say, 5 million, right? And then recompute everything just to remove another edge for 5 million. Maybe I remove 100 edges at once, right? That will speed up the process. And also, there's got to be some termination condition. Question mark. Like I have to decide, like in k-means clustering, or in hierarchical clustering, how aggressive do I want to be removing edges? Because the more edges, if I remove all the edges, every single node would be its own community. I don't want to get that far. If I remove too few edges, the communities are too big. So either I have a goal like in k-means, I want exactly 100 communities. So when I get to 100 disconnected components, I stop. Or I have some evaluation measure that says, if something looks dense enough as a community by some measure, like it has a lot of edges, I know the total number of edges that can appear within k nodes is k choose 2. So if I see close to k choose 2, or on the order of k choose 2, I say stop that one, that's a community. And keep going, breaking some other stuff that's not so dense. Right. So I have to find a way to terminate that makes sense, either by some inter-local notion that stuff seems dense enough, so don't break it, or by setting up in advance how many components do I want.
So when you do in batches, right, if you remove 100, isn't it wrong? I mean, you have to actually recompute before removing one. So if you're removing 100.
True. Yeah, I have to recompute after each one. But if I have a graph of 5 million things, that may take a long time, right? I'm just saying some speed ups are possible. What's the danger in removing the top 3 edges? Instead of removing one edge, I remove the top 3. The problem is not the update, right? Once I remove 3 edges, I can do the update. The update will make sure I recalculate the scores correctly. What's the danger in removing 3 edges or 5 edges or 100 edges at a time? Theoretically speaking.
3 of them might not be one.
and when I beat the edge that I want to remove, right? In other words, I know I want to remove 100 edges, but the edge number 2, once I do the update after removing number 1, magically is not a bottleneck edge anymore. Is that likely to happen? So if an edge was a bottleneck initially, can out of a sudden after one removal, so I have, this is a bottleneck edge, this is a bottleneck edge. Maybe there's another bottleneck edge here. Is it possible that once I remove this, or likely, I want to say possible, I say likely, is it possible that if I would recompute the score of the other edge, that was my second edge, this is the number 1 bottleneck, right? This is the number 2 bottleneck, this is the number 3 bottleneck. Initially, with the initial computation. But I just said, I'm going to remove all 3, right? Number 1, 2, and 3 without updating. I'll update after I remove all 3 edges. Why that can be wrong? Because if I just removed 1, like the algorithm is saying, and I do the update, maybe this one would out of a sudden not be a bottleneck edge. Is that likely to happen?
What if 2 edges are connected? Like that's the only path.
What? Like in here?
Like they're connected one after the other, and that's the only path. So both
Like
of
in
them-
here, the path
Yeah.
from here to here?
Yeah. Between 2 communities, there are 2 edges.
So you mean something like this, there's a large community here, I'm gonna say a bunch of nodes, this is all community connected. There's a large community here, and in between them, there's just 2 nodes.
Yeah, something like that.
So now, they are saying, what are the highest bottleneck edges? 1, 2, and 3, right? Something like that? So you're saying, if I would remove 1,
There's no connection.
maybe this is not counting as a bottleneck edge anymore. I don't think that's likely, even in this case. I think even in this case, I mean, just my personal intuition that even if I remove this and update immediately, the bottleneck edges won't happen inside here or inside here. It will still be one of those 2.
But there is no connection.
There,
There will only be paths from here. Now I removed this edge. There will only be paths from here to here now. True. But I still think this looks more like a bottleneck to me than some edge inside the component. So I think I don't want to argue theoretically here. I don't want to make a proof. All I'm saying is, it seems to me, maybe I'm wrong. Well, why don't you prove me wrong? I'll give you an extra credit. My intuition says that you don't have to remove 1 at a time. You remove few at a time, maybe not like a million of them at a time, but few at a time. You perhaps can update just every once in a while.
Say you have that edge from J, from J to like inside.
This?
Yeah, the next edge on its right.
Yes.
Yes, that was a bottleneck too, and you removed number 1, then that won't be a bottleneck anymore, right? Because if every path from the first community had to pass to that edge, from J to the one after that. So it was a bottleneck before, but after you remove 1, it's not a bottleneck anymore. So more than that.
But why is that? I don't understand the setup. In this, you mean in this setup?
Yeah, so
In this setup, this is not a bottleneck.
say
right?
it is like that's the least and everything passes through that.
Yeah, like in here, you mean?
Not like that, just like
Maybe 1 node, and we have 2 edges.
not
Both
like
of them
that.
are bottleneck.
Yeah, not like that. There, like there itself. Say the one from J on its right, that edge is a bottleneck.
This.
Yeah.
But
Because
this
that's
is
a
the
small-
same like in here. To be a bottleneck, it has to be
Yeah. Okay.
forcing paths through it.
So if that was the minimum edge, it will still force pass through it, right? If that edge has really low weight, then it would.
The low weight is not what the bottleneck means.
No, like a forcing pass through it is like, for example, like here. If you have to go through it, if it has a low weight, everything will go through it, right? Isn't it like that? Or am I understanding it wrong?
If it has a low weight, more shortest paths will go through it.
Yeah, so that would lead to it becoming bottleneck,
Right, but it doesn't mean there's no other shortest paths. But that's, I think it's independent with the discussion about removal.
right? So if in that case that was a bottleneck, say everything had to is passing through that, that's a bottleneck.
I removed it.
You removed it, then it doesn't it is not a bottleneck anymore. So then
Right,
so
but
that-
the edge is gone if I remove it.
yeah,
Right?
so that won't.
But
be a
then
bottleneck
the
anymore.
other edge that was a bottleneck, my intuition says that still should be a bottleneck within the disconnected component. Of course, now if this was the only path, maybe that's what you're saying. There is no path from here to here anymore because I just removed that edge.
Yeah.
True. But if this was a bottleneck, wouldn't be still a bottleneck between the remaining connected components here?
I think to prove this, we only need to prove whether you remove one by one versus remove a batch will change the ranking of the betweenness score, right? If the score is changing, you remove two, then the third
The
one.
score will change
Yeah.
numerically.
As long as it will change, then it depends on how you define the bottleneck.
But the ranking, he's making a good point. The ranking may not change that much.
Yeah.
In ranking, especially in the information retrieval, they study ranking a lot. We call ranking changes local changes that has to do with ranking is almost the same, but some things are reversed, which we don't bother too much, or global changes that change the ranking massively.
Yeah,
So my intuition is that you could have some local changes, but not big global changes. An edge that was not a bottleneck initially was way down in the scores of bottlenecks, cannot suddenly come up. But that's just my intuition.
Yeah, so if like something in a very borderline, right? So like number 100 before we
No, number 5 million.
Yeah,
If
so
I
so
find
in
it.
in practice, it may not be a big issue because the number.
That's
is
what
very
I'm
high.
saying.
Yeah.
I'm not looking for a mathematical proof here. All I'm saying, if there's 5 million edges, and I estimate I may want to remove about 1 million of them to get communities. I think removing 100 at a time and doing this 10,000 times to get to 1 million, in practice will probably give me very similar results to removing one at a time in terms of the groups that I end up with. Now I'm not sure that's true, just my intuition. You have to implement the algorithm, so we'll see if you take on batches or not. All right, so that's this algorithm for finding communities. I want to mention 2 other things that are quite popular, but not in your homework. One is a heuristic, and one is something that relates to many things we already have seen. So finding community is one thing. These sort of algorithms here, so if we say finding communities, we have these algorithms like Garvin-Newman type of algorithm that's based on shortest paths at scale, let's say. It involves a lot of traversals in the graph and a lot of updating of the graph, if you like, right? Then we have other algorithms that are based on linear algebra. There's one in the book. Factorization or decomposition, and eventually eigenvectors. Both these are slow type of algorithms. Now, I'm not saying they don't work well, they do, but they're slow. For the obvious reasons. The algorithm matrix is very big, so working with a linear algebra operation on that matrix is hard. Or this kind of thing requires shortest path computations, which are not an easy thing. Shortest paths are often like V squared E type of thing, and if you have to do it a lot, that scales pretty quickly. So people have thought, okay, can I do something, sacrifice a little bit of rigorosity, kind of follow my intuition, follow some heuristics, but get something much faster, right? So how can I sacrifice rigor math, but speed up. So if you like, this is the negative part, this is the positive part. So this is the same like in hierarchical clustering. Why hierarchical clustering works very fast? Remember how hierarchical clustering goes? I group the similar items that appear similar at the locality level, and once I group them, I don't change my mind about it, right? So once I group the similar items at the base, then I keep going and just build the hierarchy all the way up, and I never go back to change my mind. So based on this idea, let's see, this is here. It's called Medis. Must be here somewhere. Where? So like I said, there's quite a few algorithms that people understand theoretically, just slow to run. And I would add there's another big problem that the book doesn't talk much about it, which is a very modern research problem. PhD thesis written now about it, which is the problem of embedding. If I have data like users or movies or images or cities or patients or emails, but I don't have features for it. So normally if I have features, that's my X space, the embedding space, how I control the data. But if I have other type of information about my data, for example, the fact that this patient is more sick than that patient, or this city is closer to that city than the other city, or things like that that are not giving me an explicit representation of those objects, right? All the data sets you had so far came with a very explicit representation. An image is a bunch of pixels with colors in them. An email was a bunch of 50 features with values. A document is a bunch of count of words or something like that. Suppose I don't show you the document or the patient or the email. I'm just telling you this is more sick or less sick than this other person. Or I like that movie better than I like the other movie. There is no actual rating. I'm only saying I like that movie more. In a lot of problems, this happens very naturally. For example, currently at Spotify. People have preferences over the songs. It's very hard for Spotify to have actual ratings. They don't know how much I like a song, but they know I like these songs better than the other songs. It's been shown a lot of times in research settings that preferences are much more reliable than actual ratings. When people put 1, 2, 3, 4, 5, they mean usually random things. Everybody has a bias. So it's hard to interpret a 4. If I put a 4, she puts a 4, there might be different meanings of what we mean by a 4. But if we say I like that movie more than the other movie, it's been shown that that's a very consistent notion. Okay? So for this reason, the embedding problem, it's very important. And so people have struggled with how do we get a bunch of feedback, clicks, preferences, whatever people tap in, right? Sometimes people put a search and they see a bunch of results and they click on the 4th link. What does that mean? It means the other 3 are no good? We don't know, right? So a lot of big platforms like Google and Apple and Facebook, they have a lot of data, but they have to manage reliability of this data. How certain can they be that a click means that that document is good, right? So embedding is a big problem. And in embedding, this phenomena that I'm describing here, it's exaggerated. It's a much more than in the social phenomena. That is, We know theoretically how to solve the problem. We have some algorithm and it's going to give us a good embedding, but it's extremely hard to run that at any scale. Just recently we have a PhD student that's going to graduate and he works in embedding problems. And because of him, we looked at a bunch of academic papers. Up to the year 2017, the data sets for each embedding theoretical and mathematical provable algorithms work have like 60 objects. Imagine you're Spotify and somebody in the year 2017 says, I have an embedding algorithm I can demonstrate to you works on 60 objects. And your Spotify will say, sorry buddy, I don't care how good your algorithm is, because if it only runs on 60 objects, I can't use it, right? So we need algorithms that runs on thousands, hundreds of thousands, millions of objects. And currently mathematics and what's provable, it's at around 60 to 80 objects. Clearly, it's a big gap between what we can prove correctly with an algorithm and what we can do, what we need to do in practice with the data sets we have. Now, people have speculated, for example, that quantum computing, if it works out, it's going to exponentially scale 60 to, I don't know, a few million. That's a speculation so far on two fronts. It's not clear that quantum computing can speed up exponentially at scale. It can go from 2 to 4 to 8 to 16, but can it keep going until I reach millions? Right? So that's something you guys can read about quantum computing. It's not clear to me and to people smarter than me that this exponential that happens at low scale can actually keep going at high scale. The other thing, of course, that's not clear about quantum computing is when it's going to stop being a fantasy and it's going to become a reality. There is a computer at MIT that uses now 6 quants, and one at Berkeley that uses 5, and they upgrade to 7. It's not clear when that's going to become, and every year there's a talk that says by next year it's going to be big and it's going to be commercial and it's going to change the world, right? So that's happening since 20 years ago. Again, if it happens, and it might happen, this is a very realistic possibility that we figure out how to scale exponentially instead of linearly or polynomially. We can break into cryptography, solve a lot of interesting data problems, so on and so forth. But until then, we're going to have this problem that what we can prove and work with doesn't really scale. So what do we do?
The math.
Right. We want to do something in between that has a good chance of working. It's reasonably on resources, so we don't need to have a super infrastructure to run it. But it's not too far from what our intuition and proof says. So the plan would be to modularize the data, or the graph in this case, and try to apply these algorithms at different levels of the graph. So that's the idea of hierarchical clustering. We go from the bottom and we keep going up to the top where we have only so many hierarchies or clusters, and at that level we can do some classification or some data interpretation. Instead of having millions of items, I only have 300 items. I can run something, and then once I have that, say, classification run at that higher level, I can keep down and say, maybe given that classification, keep going down. See, think of an ontology, right? At the bottom it's very big, but I go up to some top and I do some inference. Which one of the main classes are likely to be patients readmitted in the hospitals? That one and that one and that one. It's easier because there's only 300 classes at that level. But then once I decide that, I can go further down in class and do some exploration based on the hierarchy I have. So this is the kind of mechanism we want to apply for graphs. How about, here's an example from the book. Here's how the graph looks like. I have to take a good look at those edges. So the edges I have here are 4, 1, 2, 1, 3, 4, 3, 1, 1. So the idea of grouping stuff together would be to create what's called a factor graph, where each one, similar to the components, each one of the new nodes will be a bunch of the old nodes. So here's the proposal. Suppose I figure out the way to group those, and I figure out the way to group those, and I figure out the way to group those, and this remain its own group. Now, I'm not discussing how to group them yet, but if I do that, what should I have? I have now, I'm going to draw this some squares. I have a square that represents those two nodes here. Right. Another square that's a, let's call this, let's give a name, A, B, C, D, E, F, G. So this square represents AB now. This square is CE. This square is DF, and this square is just G. Now, what should I do about the edges? What edges between AB and CE? Suppose those are similarities. So the reason I group those is because they have a high similarity. So let's say in this case, these are similarity. You can use distances, take 1 over the distance, get a similarity. Right? These are similarities. I group them because they have high similarity. Not sure why I wouldn't group those now. Anybody can give me a quick idea why, since this is a 4, wouldn't be better to group those two? What would be the problem if I group those instead of these two? Why do you think the book, as an example, group those that are similarity 4, but not those at similarity 4? Anyway, that's a question for later. Suppose I group them that way. What should be my new similarity between CE and AB? There's an edge here, but that's an edge now consisting on all edges between AB and CE. So an example here is to use 1 plus 2. Why 1 plus 2? Because there are 2 edges there, right? So if I use this mechanism, what's between CE and DF? 1 plus 4, right? Between this and this is what? 1. This would be. And this between C, what is AB with DF? 1. AB to DF is just this edge. So one thing it's easy to see. If you manage to do this and you're happy with the grouping, this would be a much easier graph to do anything with it. In fact, these kind of algorithms are like hierarchical clustering. They keep doing it. They say, this is G0. That's the original graph. This is G1. But then I can keep this process to G2, to G3, like in hierarchical clustering, until at the very, very end, what's going to happen? Everything, if I keep down, everything will be one node. That's Gn, when I group everything together, right? Like in hierarchical clustering is not useful to be, I mean, I could build the whole hierarchy, but at some point I have to decide how do I run my algorithms. My point being, a lot of these algorithms here, and the embedding ones, and some other ones, might be easier to run on a higher level graph. And then, if I decide something about this component or that component, For example, in community detection, I may say at this level, those two form a community for some reason. Then I know I don't have to go down. Everything in those nodes form a community. This graph might be a lot easier than the original graph to work on. So, of course, that's all nice and easy, and I think everybody can see that. Where is the problem, the tricky part? Tricky part is in building those graphs, right? You have to know sure you're going, because this is not changing your mind, right? Like in hierarchical clustering, if you group the two things that you don't want to group, they're going to be grouped all the way up. There is no way to go back and change your mind. Same thing in here. If there was a mistake or something that didn't go well, it's going to continue going like that all the way up. So what people need to do here is to find a good heuristic. For grouping. Grouping is the common English word, but in graphs we call it factoring. A factor would be, this is a factor. Once I have, a heuristic cannot be perfect, but once I have a good heuristic, it will allow me to run. Again, it's no theoretical guarantee that things would work, but it will make a lot of these algorithms much faster because I can run it on much smaller graphs, including the ones I told you about, the 60 part of this PhD student work is to apply that algorithm for general graphs. How do you think he does it? I have a big graph. It has, 60,000 images with some dependencies between them, or patients, or documents. And there's an algorithm that says it can do embedding in his case, but it only works with up to 100 objects. So what should I do? Apply some heuristic to factor the graph up to the point where I get 100 nodes or less. Then start calling this embedding algorithm, right? I can do it because it works at that scale. Once I embed this graph, I'll have a representation for each component. Now I can go down and say, okay, within that representation, say that's 300 values. My representation is on 300 dimensional. I could say, add another 100 dimensions just to represent everyone in that component, maybe. So I can do a localized, call again that embedding procedure, only within AB. So that is respecting the AG preferences or edges or something like that. So by creating this hierarchy, we can run complicated algorithms on smaller scale, and they will be successful with the condition that the hierarchy is not messed up early on. Same like with hierarchical clustering. Later on, it's easy to do good clustering if the bottom of the hierarchical clustering is not mistaken. So I wanted to mention that idea as a general idea. I don't care about looking for these exact problems, and the book has some heuristics for how to do this. I want you to remember a way to go around the scale problem when the math is complicated. You look at your algorithm, if it's something linear or logarithmic, you probably won't have a scale problem. Most of those problems are easily parallelizable. So if it's linear or logarithmic, you can probably use multiple threads, multiple computers to do the job. But if you see a v4th or v squared, e squared, or something like this, there's little hope that that algorithm can ever run on Facebook graph. It's impossible. V squared on Facebook graph is just not going to happen. So you need some heuristic to break up the graph into smaller parts or to group it into factors before you start running procedures like that. Heuristics means you don't preserve the original guarantees of the algorithms, like optimality and what they do, so on and so forth. But in practice, if you have a good heuristic, many times things just work. The other thing that I want to mention here is something we already have seen, but it's just written, the same equations are written in just a different way. I'm mentioning it because this is a basis of many algorithms. That's why we've seen it before. the following idea. I have a graph, and Wij is the weight of edge ij, and I have an objective. I want to embedding or classification of every V vertex into some f of v being that embedding. If it's classification, f of v is probably sick or not sick, or black or white, right? Classification asks you for a function that gives the class. In a multi-class setting will be which one of the 20 newsgroups category will be that. That'll be 1 out of 20. In MNIST will be f of v will be one of the digits, right? 0 to 9, something like this. In an embedding setting, we ask for an embedding of k dimensions. If you know word vectors embedding or images embedding, so on and so forth, that has the following property. So I'm going to say just f of v, there generic, with the objective that wants to be minimized. Sum over ij, wij, and some delta f of I minus f of j, say squared. We've seen this approach before. I think even k-means had some objective that can be written like this, right? So I know we've seen this before, and we talked about before. It's very natural for graphs to think this way. Whatever my f is, could be a classification function, could be an embedding function. What is this really saying? This is saying two things. When f of I minus f of j is big, if you put I and j as an embedding or classification, very different to each other. You can do that if wij is, remember I want to minimize this thing. So in a minimization, when can this one be big? When wij is small. If wij is small. And here, we treat this as similarities. So we're saying with this kind of objective, if there's not much similarity, or maybe it's dissimilarity, remember sometimes those goes backwards because things are like users are anti-similar, then you can afford a big distance here. And when wij is big, that means similar. When two items appear close to each other, whether by distance or by characteristics or by symptoms, whatever it is, then we want them to be embedded very similarly. So if you follow, there's many problems that have this flavor. Word embedding. How do they assign? You know, word embedding assigns a bunch of values for every single word, right? The criteria is a criteria like this that says if words are similar, appear in the same context, in the same documents, next to each other, whatever the similarity is defined is, then you want the embedding to be close. And if words are not similar, you can have them far apart. Okay? So we've seen this with, I think, k-means and other factors. So there is the theory that says, what does it say? Take, it's called Laplacian. I don't even want to say the name, forget about the name. L is a diagonal matrix minus W, where this diagonal, so W is the edge matrix, this diagonal only have elements on position II, and that's the sum of, for I is the sum over j of wij, so it's kind of an average, I think, 1 over n, something like So there's a diagonal matrix means that. I don't even need you to pay attention to what this is. My point is that this whole thing can be solved with linear algebra. There is a very simple linear algebra that says if that's what you want, you define this Laplacian, then you set up the optimization problem, minimize f transpose Laplacian f. This Laplacian happened to be a very nice matrix, one of these positive semi-definite with all kinds of nice mathematical properties. Then you can show from here that you get, did we talk about Lagrangian functions? I think we did at PCA, right? Where how you minimize something with a constraint. So you can show that, there's more math in here. The function you want is an eigenvalue, eigenvector of the matrix D minus 1 L. Now that sort of theory is the same of theory we did when we minimized those functions. It's not too easy, too hard to show that if this equation here corresponds to this equation, so on and so forth, could be solved with eigenvectors for the same reasons that PCA had eigenvectors. It is true that this in here, or even earlier, the obvious way to minimize this is to set f to 0, right? Or to a constant. If I set f to 0, this will be the minimum objective, assuming the weights are positive. And it's also useless, right? Who wants a classification that's constant 0? Or an embedding that's constant 0? So it needs some sort of scaling constraint that says, I don't want the f equals 0 solution. So we don't want f equal constant. That will correspond to something that says at the constraint, scale constraint, f transpose df equal 1. That's just scaling kind of how big the weights are. It scales the weights to be kind of regularized or normalized to something. And this constraint creates the Lagrangian that says you have to minimize the function with a constraint in it. But that whole theory, it's kind of something that I'm sure you can follow. My point is, this can be done linear algebra quite exact. I mean, the coming up of f in here that says an eigenvector, and it's the eigenvector with the eigenvalue that's not 0, is the other one, the next one. Because the first eigenvalue will be 0, that's no good. In practice, linear algebra methods are not good at scale. So as an approximation, sometimes they work, but in practice, people still do it with the numerical optimizations, like gradient descent or Newton's method or something like this. So a lot of the theory could be presented nicely in algebra, but in practice, you would do something else. I want to say just one more thing about this, why it's an important thing. I think I might have talked earlier about heat equation and how heat balances in a room. That's a very important thing with graphs. You can think of a graph as some of these f's are already set for you. So in other words, this f is given, this f is given, this f is given. The value of f's, whatever it is embedding or classification, it's known for those points. So f of I is the f in a vertex. Those are fixed, those are the training set for which you know exactly what f should be. And you can't change f in those points. F is fixed in those points. So the question is now, how do you compute f's for everybody else if you have some fixed f's? That's a classification based on random walk, and it has massive implications from thermodynamics to biology to text matching even. Okay. So we have one more lecture that will be next Wednesday. And what I'm going to talk about next Wednesday, it's neither for homeworks nor for the exam. So the material you have in the homework and exam finished today. Next week I'm going to talk about something that's not in the homework or exam. I don't mean to say you can miss the lecture.